welcome everyone to this episode of Ithaca Fest. Our first speaker today is Soichiro Fujii, talking about nerves of T categories. Please.
Thank you for the introduction, and also thank you for the organizers of the Ithaca Fest for giving me an opportunity to give a talk here. So today I'd like to talk about my ongoing joint work with Steve Lack at Macquarie University on nerves of T categories. So let me start with explaining what this talk is about. So it is well known that for any small category, we can construct a simplicial set called its nerve. And this defines a free faithful functor from the category of categories into the category of simplicial sets, and we can characterize its essential image. And I will recall this fact in a minute. And the notion of small categories is generalized to the notion of internal categories in E, which is a category with provux. And it is straightforward to generalize this nerve construction from categories to internal categories. So in that case, we obtain a simplicial object, which is just a functor from delta op to E as the nerve of an internal category. And Burroni introduced the notion of T categories for any category E with provux and any monad T on E. And I will recall the definition of T categories in this talk. But for those familiar with the theory of T categories, let me mention that in this talk, I will not assume that the monad is Cartesian. Okay, and of course, when T is the identity monad, this notion of T category reduces to the notion of internal categories in E. And this talk is about the generalization of the nerve construction to T categories. So I will define the notion of T-simplicial object, and I will show that every T category gives rise to a T-simplicial object. And this construction defines a fully faithful functor from the category of T categories into the category of T-simplicial objects. And once again, we can characterize the essential image of the nerve functor. Right, and before going into the main body of the talk, let me mention that some of the famous examples of T categories. So I guess the most famous one is that of multi-categories, which is T categories in the case where the base category E is set and T is the free monoid monad. And another important example is that of virtual double categories, which is the case where E is the category of graphs and T is the free Cartesian monad. And in our recent paper, we observed that unital virtual double categories, which are virtual double categories equipped with horizontal unit on each object, can also be regarded as T categories. So in this case, we use the category of reflexive graphs, and the monad of T is again the free category monad. And in this case, the free category monad on the category of reflexive graphs is not Cartesian, so that's an example of non-Cartesian T. Right, so anyway, in this talk, I first explained this classical nerve construction for ordinary categories. Then I generalized this to internal categories. And finally, I will explain our work, which is the nerve construction for T categories. So first, the classical nerve construction for ordinary categories. So because I will talk about simplicial sets, let me quickly review this category delta. So this is a category whose objects are non-empty finite totally ordered set like this for each natural number n. So this square bracket n consists of n plus 1 elements, and morphisms are monotone maps between them. And it is well known that every morphism in delta can be written as a composite of these maps, delta I, which is an injective monotone map, which omits I, and sigma I, which is a surjective monotone map, which hits this I twice. And a simplicial set is just a functor from the opposite of this category to set. So more explicitly, it consists of the following data. So for each natural number n, we have the set xn. And of course, for each morphism phi from m to n in the category delta, we have a function delta star from xn to xm. And because, as I said, every morphism in delta is it can be written as a composite of these morphisms, it suffices to specify the images of these morphisms. And the delta I star is usually called di, and it is called a phase map. And sigma I star is denoted by si, and it is called a degeneracy map. Okay, so and that's the notion of simplicial set. And what is the nerve construction? So the starting point is that because every totally ordered set can be regarded as a category, we have a map from delta to cat, which just identifies delta with a suitable subcategory of cat. And this functor J induces this functor N from cat to delta of set, this functor category, which is a category of simplicial sets. So it maps each category A to the simplicial set NA, which maps the object N to this set of all functors from N to A. Or in other words, it is just a set of all composable strings of length N in the category A. And it is well known that this nerve functor is free spaceable, which is another way of saying that the functor J from delta to cat is a dense functor. And moreover, several characterizations of the essential image of the nerve functor N are known. And for the purpose of this talk, let me mention the following characterization. So a simplicial set X is in the essential image of the nerve functor if and only if for each natural number n, at least 2, this square, which commutes by one of the simplicial identities, is a product of sets. Okay, so to get an idea of what this proportion is saying, let's consider the case where X is just actually the nerve of a category A. So in that case, given a string of length n, this D0 sends this string to this string, so it just forgets the first arrow F1. And similarly, this Dn maps this to this, so which forgets the last morphism. And this D0 and Dn minus 1 sends this to this string of length n minus 2. So to say that this is a pullback is equivalent to saying that to give composable morphism or composable string of length n is equivalent to giving a pair of strings of length n minus 1, which agrees, which suitably agrees, and then we can glue them together to obtain this string. Okay, and also let me mention that by using this pullback many times, for example, we can express this set X4, for example, as the composite of these spans. So we have 4 spans. Each of them corresponds to the underlying graph of a category, when, of course, X is the nerve of a category. And this is also saying that X4 is a set of all composable strings of length n. Okay, anyway, that's the classical nerve construction. And let's move on to its generalization to internal categories in a category E. So for any category E, we have the notion of simplicial object in E, which is just a functor from delta up to E. And as in the case of simplicial set, such a functor consists of the following data. For each natural number n, we have an object xn of E. And for each morphism phi of this type, we have this morphism in E. And again, because the category delta is generated by these morphisms, delta I and sigma I, it suffices to specify the images of these maps. And again, these are called phase maps and degeneracy maps, respectively. Right? So that's the simplicial objects. And let me review the notion of internal category in a category E with provux. Category in E consists of the following data. First, we have an object of objects A0 and an object of morphisms A1. And we have source and target maps from A1 to A0. And because I want to relate categories in E with simplicial objects in E, I will use the simplicial notation. So the source is denoted by D1 and the target map is denoted by D0. So note that the intention is that this D1 should be the image of this delta 1 in the nerve of the internal category. And I mean, this map indeed maps the unique object of 0 to the source of the unique non-identity arrow in 1, and similarly for this one. Next, we have the unit map as part of the data of a category in E, which goes from A0 to A1, and this is denoted by S0, because that would be the image of this morphism in the nerve. And finally, we have the composition map D1 from A2 to A1, where A2 is the object defined by this pullback in E. And we require that the usual axioms of category to be satisfied. Now, what is the nerve of an internal category in E? So let me describe that construction, which is straightforward generalization of nerves of ordinary categories. So the nerve of an internal category A, which I also call this A, is the simplicial object in E defined as follows. So because we want to define a simplicial object for each natural number n, we want to define an object an in E. But A0 and A1 are given, and for each n, at least 2, we define an and also these outer phase maps, D0 and Dn, inductively by this pullback. So this pullback appears in the nerve condition characterizing simplicial sets which are nerves of categories. But by using this construction, we can define the object an and also these phase maps, outer phase maps, D0 and Dn, inductively. And actually, the case where n equals 2 already appears in the definition of internal categories. Okay, and how can we define the inner phase maps, which is di, where I is strictly between 0 and n? So these can also be defined inductively. So d1 is given as part of the data of an internal category. And for each n, at least 3, and for each I strictly between 0 and n, we want to define di from n to n minus 1. And the point is that because n minus 1 is at least 2, this is defined as a pullback. So we can use the universal property of the pullback. So we define this morphism as the unique morphism making this diagram commute. Okay, so what we are doing is that n minus 1 is defined as this pullback. So we are defining this morphism di as the unique morphism which makes this equality hold. And yeah, of course, the commutativity of these regions can be proved inductively by using these corresponding conditions in one dimension below. And I will omit the details, but similarly, we can define the degeneracy maps Si. And in this way, we obtain a simplicial object in E. And here's a fact for any category E with pullbacks, the nerve construction just described defines a free spaceable functor from the category of internal categories in E to the category of simplicial objects in E, which is just this functor category. And once again, we can characterize the essential image of this free faithful functor. Namely, the essential image consists of all simplicial objects X satisfying this condition, which is exactly the same as in the nav condition for ordinary simplicial sets. Right? So that's the nav construction for internal categories. And let me move on to the main topic of this talk, which is the nav of T categories. So I'd like to start with the definition of T category, which is due to Burroni. So suppose that we have a category E with purbax and T, which is an arbitrary monad on E. And once again, let me mention that we don't assume that T is Cartesian. And I want to present the definition of T category by contrasting it with the definition of internal categories in E. So a T category is very similar to a category in E. So we have an object of objects, A0, which is an object of E, an object of morphisms A1, which is again an object of E. And we have source and target maps. And the difference is that the type of the source map is not from A1 to A0 as in internal categories, but from A1 to T of A0. So I mentioned that one example of T category is multi-category, which is the case where E is the category of sets and T is the free monoid monad. So in that case, each element of A1, which is a multimorphism, has a single object as a target, but its source is a list of objects. Right? And the type of the unit map is the same, just add 0 to A1. And we have the composition map D1 from A2 to A1, which is the same as in the previous case, but the definition of A2 is a bit different because the source map, the type of the source map is different. So previously, namely in the case of internal categories, A2 is defined as the pullback of this diagram. But now because the codomain of D1 is T of A0, we put T here and we take this pullback. And we require the usual axioms of a category. But for example, associativity is expressed by this, the commutativity of this square. And here A3 is again defined as a pullback. But because, this D2, which comes with the definition of the object A2, has codomain T of A1, we once again have to apply T on the bottom. Okay, so that's the notion of T category, and the main question I want to address in this talk is what is the nav of a T category, namely how can we generalize the nav construction for internal categories to T categories? So because the nav construction for internal categories, we constructed the object an for each natural number n, and we want to do the same thing for T categories. And in fact, by looking at the definition of this A2 and also A3, here is a reasonable definition. So we define an and the morphisms d0 and dn. Note that the type of dn is from n to t of n minus 1. So we define this data inductively by this pullback. And this works because, of course, assuming that dn minus 1 is of this type, we can simply apply t on the bottom and obtain this and dn of the required type. Now, the picture is as follows. So previously we have pullback squares everywhere, but now only thing we can say is that these three are pullback squares, and the other three squares may not be pullbacks. These are pullbacks if T preserves pullback, which we do not assume. right? So anyway, this defines the family of objects an for each natural number n, and also the outer face maps d0 and dn. How can we define the inner face maps di? In fact, we can do the same construction as in the case of internal categories. So here's what happened in the internal categories. So D1 is given, and for each n at least 3 and I strictly between 0 and n, we use the fact that n minus 1 is defined as pullback to induce Di. And we can do basically the same thing for T categories, but care is needed because, okay, so D1 is given, and we want to define Di. But in the definition of Di from n to n minus 1, we use Di from n minus 1 to n minus 2. And we have to ensure that this Di has this type to imitate this construction. Namely, we assume that this I is at most n minus 2. And in that case, we can define this Di by the commutativity of this diagram. And when I is n minus 1, we have to consider a bit more complicated diagram, because the problem is that in this case, this map is outer face map. So it has type from n minus 1 to t of n minus 2. So we get t squared of n minus 2 here, and we have to use the monad multiplication m. But again, in this case, we can define this map by the commutativity of this diagram. Okay. And the degeneracy maps can be defined similarly. And for this, in some cases, we have to use the unit of the monad t. And let me mention that part of this construction appears in this recent paper by Boom. Okay, so this construction applied to any T category A gives rise to the following structure. So we have objects n for each natural number n, and we have these maps. So di from n to n minus 1 for each I strictly less than n. And the type of dn is from n to t of n minus 1. And the type of the degeneracy maps is the same as in the definition of simplicial object in E. And these data satisfy simplicial-like identities, but suitably modified to take into account that the type of DN has been changed. So for example, this single simplicial identity involving face maps will be replaced by 3 types of axioms like this. Okay, anyway, in this way, we can define the notion of T-simplicial object as the structure consisting of these objects and these morphisms satisfying simplicial-like identities, which can be given explicitly, but I will omit that in this talk. And using this notion, we can show the following. For any category E with pullbacks and for any monad T on E, this nav construction defines a free feasible functor from the category of T categories into the category of T simplicial objects. And the essential image of this free feasible functor can be characterized in a similar way. Namely, it consists of all T simplicial objects X, such that for each n at least 2, this commutative square is pullback in E. Okay, so but we arrived at the notion of T-simplicial object in an ad hoc way by starting from a T-simplicial category and thinking about its nav construction. And it turns out that we can give more conceptual definition of T-simplicial objects as well. So suppose that X is a T-simplicial object, then we have this data, but if we ignore this this part, these objects and these morphisms define a genuine functor from delta R op to E, where delta R op is the wide subcategory of delta generated by these delta i's, where I is strictly less than n, and these sigma i's for each I. So we do not use this delta n, which corresponds to this map dn. Or equivalently, this wide subcategory delta R can be described as the wide subcategory of delta consisting of all top preserving morphisms. And what about this remaining morphisms Dn? Because the morphism Dn from xn to txn minus 1 in E is equivalent to a morphism from xn to xn minus 1 in the class 3 category of T. In fact, using these morphisms Dn, we also have a functor x hat from delta up to the class 3 category of E. And this diagram commutes. And in fact, we can equivalently define a T-simplicial object X as a pair of functors X tilde of this type and X hat of this type, making this diagram commute where this Ft is the identity on object left adjoint functor. And similar description works for morphisms of T-simplicial objects, which I haven't defined in this talk. So for any category E with pullbacks and for any T, which is a monad on E, the category of T-simplicial objects is this pullback, which is just another way of saying that to give a T-simplicial object is equivalent to giving a pair of functors making this diagonal commute, and same description works for morphisms. Right, so that's the nerve construction for T categories, but in the paper that we are now writing, we have further results. So let me conclude my talk with these results. So we make the category of T-simplicial objects into a category enriched over the category of simplicial sets. This S-set enriched category I will call STE underlined. And we showed that this home simplicial set in this set enriched category is actually the nerve of a category whenever in the codomain we have a T category, which means that if we consider this full sub S set category consisting of all T categories of STE and bar, this is actually cat enriched, or in other words, it is a 2 category. And the 2 cells in this 2 category are nothing but T natural transformations, which are the straightforward analog of internal natural transformations. So that's all. Thank you for your attention.
Let's thank the speaker. Okay, question times is feel free to unmute yourselves and ask if you have comments or suggestions.
Okay, I have a question.
I don't know who arrived first. Okay, Paul raised his hand. Yeah, then I think Walter.
Okay, a simple question. So the last degeneracy map was treated in a different way from the others. Could you explain again why it's different?
Yeah, so the last phase map is different because I mean the definition of T category, this D1 is different. Yeah, I guess that's the reason. And so because of this, this inductive construction, since Tn minus 1 has type n minus 1 to T of n minus 2, the type of DNA is from n to T of n minus 1. Yeah, I guess that's the answer.
Sorry, I didn't really follow that. Can I ask a more sophisticated question? So often complicated constructions are adjoint to simple ones.
Okay.
Is that the case in for the nerve?
Do you mean if the nerve functor has adjoint?
Particularly one which is simple.
I mean, in the classical case, of course, we have a junction between the category of categories and the category of simplicial sets. But I guess the nerve is the easier one. The left adjoint is more complicated.
Okay, thank you.
I think Walter was trying to ask a question.
Yes. So in Burroni's original article, the motivation was, on the one hand, Lambert's multi-categories, on the other hand, Barre's relational T-algebras,
Yes.
which for the ultra-filter monad give you topological spaces. So I wonder what's happening with your nerve construction in this case. Maybe also more generally, you could ask for any T-algebra, Eilenberg-Moore T-algebra, what is happening there?
Yeah, thank you for the question. Yes, so any T algebra is actually a T category. So if we have maybe let's go B, a T algebra B, we can make this into a T category whose underlying T enriched graph is, I guess, like this. So like A1 is TB and A0 is B. We have something like this. Identity is the source map and the structure map is the target map. So in that case, actually the nerve of T algebra, Eilenberg-Moore T algebra, is related to the back resolution of this. So what we get is, in fact, in general, we get An equals to Tn of B, and the phase and degeneracy maps are basically the one we get from the bar resolution of beta.
Okay. So that's, if T is the ultrafilter monad, this would be the case of compact Hausdorff spaces. But if you go to the case that your span defining a Burroni T category is just a monospan, so that's a relational case, which for the ultrafilter monad gives you topological spaces. What's happening then?
Yeah, I haven't thought about what T-simplicial objects are when T is the ultrafilter monad, but yeah, I think that's an interesting question that we should think about. Thank you.
Okay, thank you.
Okay, and Nathanael?
I just wanted to ask whether you could share a comment or two about some of the applications of this result that motivated you to think about this problem.
Yes. So I guess one application we are thinking about is by using these T nerves, nerves and T simplicial objects, we want to get a clearer view of exponentiality of maps between T categories. T functors. Because when E and T are sufficiently nice, these T-simplicial objects can be regarded as precious over a suitable category. And since precious category is locally Cartesian closed, I think we can use that to understand the exponentiality of T functors.
Thank you.
And I guess Beppe wants to try and ask a question.
Yes, thank you. I couldn't find my right hand nowhere on the screen. So Zoom has hidden all the hands I used to raise. So anyway, my question is, thank you for your very interesting talk, by the way. And sorry I couldn't get the beginning, so maybe you already say something about this, and well, in case I'm sorry. There is a preprint, sort of recent preprint by Dominique Bourne. It's on the archive 22nd January 2024. Whose title is Claisley Categories, T Categories and Internal Categories. Maybe you are aware of it, yes?
Yes.
So the connection, what if I remember well, I read this paper some times ago. He showed that these T categories are in fact internal categories in the Kleisli. Okay, so what's the connection? Is the nerve of those T category is your nerve or something else?
Yes, yeah, thank you for your question. So under suitable assumptions, we can identify T categories with suitable internal categories in the classic category of T. And that's basically because this X is defined, it's completely determined by X hat. So yeah, in fact, we can identify ST, the category of T-simple objects, as a suitable subcategory of the category of simplicial objects in the classic category. And this restricts to T categories and categories in the classic category.